All right. So this is the limiting reactant problem. So it's scary at first, but remember, when we're scared, there's always something that's safe for us to do. And what is that? Yes, the lovely balanced equation. Let's go ahead and do that. So we have two solutions reacting with each other. It says we have aluminum sulfate reacting with lithium hydroxide, and it makes a precipitate of aluminum hydroxide. Be careful here. Make sure you write the entire equation out. So we have the aluminum sulfate, Al2SO4 3. It's a solution, so aqueous, plus lithium hydroxide, also a solution, so aqueous. And then we're going to do our double displacement. So we'll get some aluminum hydroxide. And it tells us that's the precipitate. So we don't really have to go to our table because it told us that. And the other compound there, lithium sulfate, is what's left over. And that's going to be aqueous. Okay, so in your beaker after this reaction, what you're basically going to have there is, so here's my beaker. And this is an incomplete drawing right now, but you're going to have a precipitate over here. So this will be your solid Al OH3, solid. And what will be swimming in the water dissolved there? What will be left over at the end, swimming in the water dissolving? That will be, yeah. So the aluminum hydroxide would not be dissolved. It will be just a precipitate. But which ions would be in there? So I think, so the Li2SO4, if I were to write them as ions, what would they be? Right, so we'd have some lithium swimming around in here, and we'd also have some sulfate swimming around in there as well. Okay. Now, this is an incomplete picture. There's actually one more thing that will remain in here, and you might be able to guess what at the end of the problem. So we'll come back and complete this. But it said, well, yes, water will for sure be there, but one more ion, I should have said, one more ion that will be in there, and we'll take a look at what that last ion will be. Because technically what happens in this situation is, when we do a reaction, these ions are no longer in the water because they are now trapped as a solid in the precipitate, and you could filter it out. But the ions that remain aqueous, they're still dissolved in the water. You just don't see them as solids. You see them at, well, you don't even see them at all because they're dissolved in the water. So there is one more thing that's still in there. We'll see that afterwards. So right now, though, that is what we could assume is in there. So we have to write down our information here. We're going to go ahead and put, we have 30 mils, so volume, 30 milliliters of the lithium hydroxide, which is about 0.03 liters of it. And our concentration is 0.0185 moles per liter. And then over here, our volume is 20.0 milliliters, which is about 0.02 liters. Now, you should maintain the integrity of your significant figures. So, for example, here I didn't put 3 sig figs, but I should have. I'm just going to remember that I'm counting that as 3 sig figs, and here's 3 sig figs as well. Just remember that. Don't think this is 1 sig fig now all of a sudden. Sig figs need to be consistent when you're doing your unit conversions. So let's go ahead and, all right, we also have a concentration here as well, 0.0150 moles per liter. And then the question's asking for the theoretical yield of the precipitate, which is aluminum hydroxide. Generally, when we say theoretical yield, we mean basically the mass of the aluminum hydroxide that's produced. That's what we're looking for there. So before I do anything else, I'm just going to do the molar mass quickly. So I have 16 plus 1.01 times 3 plus the aluminum, which is 26.98. We get 78.01 grams per mole. So, to find the mass of aluminum hydroxide, which basically is a theoretical yield, what am I missing from the formula there? Right. Okay, good. So I'm missing moles. How can I find the moles of aluminum hydroxide? A mole ratio. Okay. So, but which one do I use? Do I use the aluminum sulfate to help me or the lithium hydroxide? Or what should I determine to figure that out? Right. I have to figure out exactly, not the emergency room one, not the ER, but the LR. So I have to figure out which one is the limiting reactant. So I'm going to do method one, just to show you how that works. You can do method two or method three if you'd like, but at least I'm going to show you method one to show you how that would work. It's the simplest one. And there was also a common error with that one, though, that some students made, and I want to show you that common error. So first of all, before I find limiting reactant, or to find limiting reactant, how do I have to compare the reactants in what quantities? As not volumes, not concentrations, but moles. Okay, good. So that's going to be my second step, essentially. I'm just going to convert all these to moles. So just a reminder, C is equal to N over V. So that means that N is equal to C times V, which is equal to our 0.0150 moles per liter multiplied by 0.02 liters. And then over here, same idea, N will be equal to 0.0185 moles per liter multiplied by our volume there. And I'm just going to figure out what those mole values are. So I get 0.0150 times 0.02, and I get 0.0003 moles of this stuff. And then I also get here, I get 0.0185 times 0.03, and I get 0.000555 moles of the lithium hydroxide. Now, before I continue, there's something I did. It was horrible. I shouldn't have overlooked this. I forgot to do it. That's right, I didn't balance it. So for some of you who are going to rewatch this, you're going to be like, no, go back, balance it. Like you're watching a horror movie and telling someone, no, don't go that way. Don't go in that room. That's where the monster is. So yeah, I need to balance this first before I continue. Because right now it didn't make much of a difference, but it will when I try to compare my mole values to try to figure out what my limiting reactant is, and then afterwards to try to figure out what product is made. So let's take a look. I can do 6, 3, 2, and 1. I think that works out. Yep. Okay. So let's go ahead and do method one. So step 3 here is find LR using method 1. You could do method 2. You can do method 3. Method 1 is just more straightforward. So I'm first going to compare my mole values on equal terms. Right now they're not really in equal terms because I have 1 in 6 ratio, 1 in 6 coefficients in the front. So I'm going to divide the mole values by their coefficient. And so I'm going to do the 0.0003 divided by a coefficient of 1, and I'll get 0.0003. Same thing. Okay. Now, for lithium hydroxide, I'm going to do 0.000555 divided by 6, and I'll get 0.000925. So, based on these numbers, which is my LR? So not the emergency room. Right, LIOH, exactly. So basically, since the 0.003 is larger than the LIOH, which is 0.00925, LIOH is the limiting reactant. So this is my LR. Okay. So students who use this method, they did a great job up until here. Avoid this mistake. We want to use the LR to find the product. Don't use the value that you found here, that you divided by 6. Okay? Don't do that. Go back and use this original value when you're doing your mole ratios. Okay, so make sure you're doing that. So you got to go back and use it. And you didn't lose a ton of marks. It was just like, make sure you do this better next time. That's it. Okay, that's right. For method 1, we just did this to find what the LR was. Now we're going back. We're pretending that wasn't even there. We're going back just to use our original values here. So we're going to go and use our mole ratio between the LR and the AlOH3 to find how much AlOH3 is made. Okay, so let's go ahead and do that. So use LR to find theoretical yield, theo yield. What is the simplest ratio between LR and the AlOH3? Right, it's 3-to-1 because 6-to-2 is the same thing as 3-to-1. Okay, so simplest ratio, there's 3 LiOH for every 1 AlOH3. And so we can use that mole ratio now. We can do, there's 0.000555 moles of LiOH. Multiply that by 1 mole of AlOH3 over 3 moles of LiOH. So we're basically just dividing by 3, right? Because it's a 3-to-1. So it's divided by, because if you go from 6-to-2, you divide it by 3. From 3-to-1, you divide it by 3. So we're just dividing by 3 to follow that same recipe. And so we cross out moles of LiOH, and we get, so 0.000185 moles. Yes, go ahead. Have a good weekend. All the recordings will be there so you can catch up with this example afterwards. And just take a look at the calendar for other homework. Take care. All right, so for anyone else doing this with me, did you get that same number? I just want to make sure it's on. I didn't make any mistakes there. All right, perfect. Thank you. So we're almost done. We have one more step to do. What's our last step here? Right, now we just need to find the mass using that formula up there with the molar mass. Okay, so now we can do our mass is equal to the moles times molar mass, which is equal to 0.000185 moles times the 78.01 grams per mole. Moles cancel out, you're left with grams, so times 78.01. I think that was right. I should remember this. Let's see. There we go. Okay. And we get 0.014438185 grams, or approximately, let's see our number of sig figs here that we used. Is it 1 sig fig? Well, okay, I see what you're saying. Yeah, so I know here it looks like it was 1 sig fig, but always go back to refer to the question because you preserve the sig figs integrity, meaning that, when you convert, it should still count as the same number of sig figs. So I think the smallest number we used was, got it. Okay, got it. Yeah, that's right. Yeah, so 3 in this case. Because I don't. No worries. Yeah, it happens. So just because this counts as a sig, because we have a 0.0 there, so those are sig figs there as well. These are all sig figs here. So are these. So are those. These here. Yeah, perfect. Yes, a lot of rules. But you're all really getting better at sig figs. Like yes, we get confused once in a while, but we're at the point where before it was what are sig figs to, okay, is this correct? And you're kind of, a bit uncertain, but at least you have the idea to look for it and you're all getting better at it. So I can already see the improvements Yes, the angry crows coming to hurt us. They made up the sig figs. I know they did. All right, so we would have 3 sig figs, so 0.0144 grams of the AlOH3. And so that would be the amount of precipitate produced. So this solid, if you were to take it out, dry it up, and weigh it, you would get 0.0144 grams of it roughly on your balance. Are there any questions about that part so far? So this was no different than what we did previously. It's just that the main difference here was that we had to find a limiting reactant first. Now, before we finish off with this question here, I said there was one more ion remaining in this solution, right? We said the aluminum hydroxide is trapped, but there's lithium swimming around and sulfate swimming around. Okay. What would be left in there as well? Right. So remember how we have the ER here? Okay, we have the excess reactant. So the excess reactant, you'd have a whole bunch of aluminum trapped in the precipitate, but there would also be some leftover aluminum there. If it was a perfect reaction, if it was like a perfect stoichiometric reaction like this one over here, all of the ions, barium and sulfate, would be trapped in there, no barium and sulfate left at all. The only thing left in your solution would be like this. This would look like this over here. So this would be your solid, your precipitate, BaSO4, solid. And then you'd have some leftover ions swimming around, some sodium plus and some chloride, okay? But that's it. Everything was used up. Everything that was there was trapped in the solute except for, in the precipitate, except for the Na and the Cl. Here, similar idea, you'll have your Li and SO4 swimming around, but there's excess aluminum sulfate. So there will be some leftover aluminum swimming around there. So we'd have to account for that as well. This is from the unreacted. From unreacted excess. Okay. So I'm going to add a little extension. Now this is mostly an enhancement. So the gifted section will typically look at this enhancement, but I do still want to show you it because it is still important to understand how to do. And we do have a little bit of time, so I want to show you how you would do this type of problem if you did see it. Okay. Because some of you are planning on taking the grade 12, and it is an important concept there. So you'll notice I highlighted in green. It is considered an enhancement concept that I'm going to just add on to this next. I'm going to briefly show you what it looks like, and then you can watch the video problems there to do it. So just to show you, if you go back to our little stoichiometry presentation here for solution stoichiometry, there's 2 videos, really good videos. But in those videos, there's 2 questions that ask for what's the remaining concentration of the ions there, or in this case, it's question D, and that's more of a challenge. So I did say it's typically for my gifted section, but like I said, if you're taking grade 12, it's still important to know. So I do recommend you try it out as a challenge to make sure you want to try to understand it. So I'm going to walk you through the general idea behind it, and then you'll be able to finish it up with the videos that are there. Okay, but for now, your main focus should really be on understanding the basics and then doing the challenge after. So think of this as like a little aside or extra or addition. So I might ask you, what is the concentration of the sulfate ions after the reaction has happened? Okay, so I might say, after the reaction has happened, what's the concentration of the sulfate ions. So basically I want to know what's left over in our beaker there. So our question is SO4 2- concentration after the reaction occurred. So our formula for concentration is, remember, C is equal to N over V. Now, after the reaction, what is our volume going to be? What's our volume going to be after the reaction? So think about what I did in this lab. It says I mixed 20 mils with 30 mils. Right. So if I ask you a question where I mix some volumes up and I ask you for the final concentration at the end, after you're done mixing, you have to keep in mind that you have a new volume. Your new volume, I'm going to call it V new or V final, is going to be your 20.0 plus your 30.0, and you'll get your 50.0 mils there, which is approximately, so 50.0 mils is approximately 0.05 liters. Okay? Again, I didn't write all sig figs there, but there should be 3 sig figs left over there. So I have my volume. What do I need to find now? To use the concentration formula. The moles, exactly. Moles of sulfate. So here's the interesting thing. Notice how I have the moles of aluminum sulfate here. Sulfate didn't go into a precipitate. So whatever moles of aluminum sulfate or sulfate I have here, I should have here as well because they stayed in the solution. They didn't change. So in other words, if I find the concentration of the sulfate in aluminum sulfate, or the moles of the sulfate in aluminum sulfate, by doing this, I can use that as my moles of sulfate that's in the solution because it didn't change. It remained aqueous, right? So for example, I found the number of moles was 0.0003. So N is equal to 0.0003 moles. So what would my number of moles of sulfate be? How could I do that? Just a quick little operation. Based on the ratio. It's a 1-to-3 ratio. Because I asked you for sulfate here. Like that was just an aside question. So you could just do times 3. So you're 0.0003 times 3. And you get 0.0009 moles of the sulfate. So essentially, step number 1, find out the moles of the sulfate that would be there. Step number 2, find your final volume. Step number 3, we could do our 0.0009, so concentration is equal to that, moles over 0.05 liters. And we would get about 0.018 moles per liter, or approximately we said it was 3 sig figs there, so 0.0180 moles per liter of sulfate. That's my concentration of the sulfate. And so you could do the same thing for, let's say I asked you for the concentration of lithium that stayed behind. How would you do that instead? The question would be very similar, but what would you do instead of, how would it be different from what I did for the sulfate staying behind? Which dissociation equation would I have to write instead here? If I asked you for leftover lithium. Yeah, you write a dissociation equation for lithium hydroxide, find out your moles of lithium, and then just divide it by the new volume, which you found over here as well, right? The 0.05 liters. The only one that's a little bit trickier is if I ask you to find the volume of the excess. And that's the one that's a little bit more challenging. And you can see it in the little challenge video that's included there. You could try to think about how you would solve it yourself to see if you could figure it out in the challenge video. Okay. So just to finish off, because it's about time to go, I want to go over the homework. So if you take a look, we have our solution stoichiometry. You can go through the examples again to make sure you understand the concepts. The learning goals are here. So if you open the learning goals, you can see the homework for that particular lesson here. So stoichiometry and solutions. You can see it next week. You do have a quiz coming up, and that quiz is going to be on Tuesday. We didn't have time to do this activity. We will do it next week. And if I did do it with the class, we'll recap it. So one of my sections did do it already. And in terms of the question that we have there about would this be on a test, it's possible to see a question similar to this extension one over here on a test, but you probably wouldn't see one where you have to find the excess ions on at least this quadmester on a test. So I would maybe know how to find what's left over of the ions, but not so much of the excess. And the videos that are over here go over that very well. But if you do see a question like this, it would be a quick one. It wouldn't be one that's worth a lot of marks. I would focus more on the other stuff first. Focus on the other stuff, understand that, and then if you really understand the other stuff, you'll be able to pick up this stuff a little bit more. Okay? Perfect. Are there any other questions? Let me know if there's any other questions. And I will post this final recording in our notes so you have access to it as well. All right. So if there's no other questions, you are good to go. And I will see you all on Monday. Please have a